This problem appears simple, but there's a hidden trap waiting for us that reveals a deeper mathematical concept. Let's explore every aspect of its solution. We are asked to solve for x in the equation. The quantity 4 minus x squared divided by the quantity x plus 2 equals 4. The most direct approach is to simplify the expression algebraically. We start with the original equation. The key to simplifying this lies in the numerator. The expression 4 minus x squared is a classic difference of squares, which can be factored. The difference of squares identity states that a squared minus b squared is equal to the product of a minus b and a plus b. Applying this with a as 2 and b as x, we factor the numerator into 2 minus x times 2 plus x. Now, we see a common factor in the numerator and denominator. Our instinct is to cancel them. However, this action is not free. We are only allowed to cancel a factor if it is not equal to 0. This introduces a critical restriction on our variable x. This means that whatever solution we find, it absolutely cannot be -2. With this condition established, we can proceed with the cancellation. After cancelling, we are left with the much simpler linear equation, 2 minus x equals 4. To isolate the x term, we need to subtract 2 from both sides of the equation. This gives us -x equals 4 minus 2. Evaluating the right side, we find that -x equals 2. Finally, multiplying both sides by -1 yields x equals -2. And here we have a problem. Let's confront the issue head-on. Our algebraic process produced a single result, x equals -2. But this result directly violates the condition we established was necessary for the algebra to be valid in the first place. This is called an extraneous solution. It's a mathematically correct result of a simplified equation, but it's invalid in the context of the original unsimplified problem. A graph will provide clear visual proof of this situation. Let's plot both sides of the equation. A solution exists wherever the two graphs intersect. The right side, y equals 4, is a horizontal blue line. The left side, after simplification, behaves like the green line, y equals 2 minus x. They appear to intersect at the point -2, 4. However, the graph of the original function is not a complete line. Because of the domain restriction where x cannot be -2, there is a removable discontinuity, a hole, in the green line at exactly that point. The two graphs never actually touch. Zooming back out, we see the complete picture. There is no point of intersection, hence no solution. Calculus offers a precise language to describe the behavior at this hole. We can ask, what value does the function approach as x gets infinitely close to -2? This is the concept of a limit. A limit doesn't care about the value times the point, only the value it approaches. Therefore, we can use the simplified form to evaluate it. The limit is equivalent to the limit of 2 minus x as x approaches -2. Now we can substitute the value. The limit evaluates to 4. This confirms that the hole exists at the coordinate -2, 4, but reinforces that the function never actually reaches this point. So, what is the definitive answer? The only potential algebraic solution is extraneous because it violates the domain of the original equation. Therefore, the equation has no solution. This problem is a powerful reminder to always check for domain restrictions before simplifying rational expressions. Thanks for watching. If you enjoyed this problem, give it a like and subscribe for more. See you next time.